Hi, welcome to this lesson on calculus, the factor and remainder theorems. Let's have a look at polynomial long division. So before we do that, let us recall how long division works for natural numbers. So for example, if we want to divide 357 by 13, we can proceed using the long division algorithm. So in here we have 13, which is your divisor. That's the number you're dividing by. On the inside here you have your dividend, that's the number you're dividing into. On the top here, we're going to see how we get this number. That is the quotient. And then the side here that we'll work out will be the remainder. Okay, so the algorithm begins by saying, how many times can you divide 357 into 13 into equal parts without a remainder? So it turns out that that number is 27. Okay, because if we do 13 times 27, we get 351, which is the closest number to 357 that doesn't exceed it. So this is sort of a trial and error sort of thing. You'll do 13 times what number will get you very close to 357. So we know 13 times 10 is 130, but that's still quite far from 357. If we do 13 times 20, then that'll give us, so that's multiplying this by 2 essentially, so that's 260. So we keep getting closer and closer to 357 until we hit a number, in this case 27, which will give us 351. So notice if we go overboard and do another 27, it will be something larger than 357. Alright, so if we did, for example, 13 times 28, we get 364, which is much larger than 357. Okay, so then the algorithm says take that and multiply the quotient and the divisor together, and then we get 351, and then we subtract that from the dividend, and we get a remainder of 6. So now this number is smaller than your divisor. So we say the degree is smaller, essentially in general, and we'll see what that means for polynomials. But in this case, the number 6 is smaller than 13, so that is the remainder. So 357 divided by 13 is 27 equal parts with 6 remaining out of 13 parts. Okay, so that's how the long division algorithm works for natural numbers. Taking that logic now, we can extend it towards polynomials. So this polynomial here, x squared plus 5x plus 6, we can divide that by another polynomial, x plus 2. So here's our divisor, our dividend. So now we ask ourselves the question, what do we need to multiply here in the quotient to get this x squared term? The goal is to cancel out these terms as we go along the algorithm. So if I multiply x by x plus 2, I get x times x is x squared, and x times 2 is positive 2x. Now notice I put brackets around that entire expression because the algorithm tells us that we must take from that dividend and subtract it from that entire quotient part that's been multiplied by the divisor. So now x squared minus x squared gives you 0 amounts of x squared. 5x minus 2x gives you positive 3x. And then anything that's left over must be brought down. So we have 3x plus 6. And then we keep repeating the algorithm because that's what a mathematical algorithm is. It's a list of rules that you follow from start to end given a certain instruction. So now I say, what do I need to multiply this x plus 2 by to get rid of this 3x plus 6? Well, if I multiply by 3, so 3 times x is 3x, and 3 times 2 is 6. Now, if I subtract that, 3x minus 3x, that's 0x, and 6 minus 6 is 0. So here, this number 0 is a constant. The degree of a constant, as we saw, is 0, and the degree of this polynomial x plus 2, well, the degree is 1, because that x has a highest power of 1. So because the degree of the remainder part here is less than the degree of the divisor, we can stop. So the remainder here is 0. So this is equivalent to saying x squared plus 5x plus 6 all divided by x plus 2. Now if we did the normal factorization of x squared plus 5x plus 6, we have x plus 2 times x plus 3. Dividing that by x plus 2, well, these are common, so they'll divide each other out, so they'll go into each other one time, and we're left with x plus 3. But that's exactly what we got when we did the polynomial long division. All right. As another example, we can divide the polynomial x squared minus 2x minus 3 by another polynomial x minus 1. So again, your divisor x minus 1, your dividend x squared minus 2x minus 3. So I need a quotient term now, that when I multiply it by the divisor, I can start cancelling terms. So I see an x squared here. So what can I do? Well, if I multiply x by x minus 1, I get x times x is x squared, and x minus 1 is negative x. So now I'm subtracting that from the dividend. X squared minus x squared is 0x squared. Negative 2x minus negative x is the same as negative 2x plus x, which just leaves you with negative 1x left over. So that's where that negative x comes from. And then the negative 3 gets brought down. And then again, we repeat the algorithm. What do I need to multiply to get rid of this negative x? Well, x I can multiply by negative 1, so that'll give me negative x. And then negative 1 times that negative 1 gives me positive 1. So negative x minus negative x is the same thing as saying negative x plus x, which is 0. And then I have negative 3 minus 1, which is negative 4. So we've arrived at a constant number, so that degree is less than that polynomial degree there, which is 1. So therefore the remainder is negative 4. So what does this mean? Mathematically, this means that if you do x squared minus 2x minus 3, all divided by x minus 1, you are left with an entire whole part of x minus 1, plus a remainder of negative 4 out of your divisor, x minus 1. And we can see that this expression is equivalent to this original quotient here. So if I do that, well, remember, these are fractions, algebraic fractions. So I need a common denominator. So my common denominator will be x minus 1 over here. So that's x minus 1 times the positive 1. Okay, so now what do I need to multiply the numerator by? Because the denominator here is 1. So to get x minus 1, I multiply the denominator by x minus 1, which means I must multiply my numerator by x minus 1. So I get x minus 1 times x minus 1. Then there's a minus separating the terms. And then 4, what did I need multiply the denominator here by? 1. So I multiply the numerator by 1. That's minus 4 times 1. Okay, so now what does that become? Well, if I expand that product out, I get x squared minus 2x plus 1, and then minus 4, all over x minus 1. But then that cleans up on the top to x squared minus 2x minus 3, all over x minus 1. And that's exactly the same algebraic fraction that we started off with. So this shows us that polynomial long division can be used to find remainders and whole parts when polynomials are divided by each other. Okay, so we're going to need this type of logic because when we get to doing cubic functions and using the remainder and factor theorems, we're going to need to know how to do polynomial long division or logical inspection when we factorize cubic expressions. All right, so that's why it's important to know polynomial long division. Cool, so let's have a look at some examples using them. I'll see you in the next one.